Hi, my name is Melvin,
My name is SH.
and what we're going to talk about today is our maximally flat low-pass microstrip filter.
We start with the design specification of the filter. Here we see that the cutoff frequency should be 4 GHz since that is a requirement for this assignment. We also set up this filter design to maximally flat during its passband. We choose 7 GHz as our working frequency to have 20 dB attenuation at this frequency. Once the design specifications were clearly identified, we then proceeded to a low-pass prototype using lumped elements using inductors and capacitor with 1 ohm normalized impedance. We then transform these lumped elements into equivalent transmission lines. With the use of CRODA identities, we could easily obtain an easy way to construct a stub design filter. After we drew initial stub design filter, we used frequency and impedance scaling so that we could calculate for the equivalent microstrip circuit dimensions. Once in microwave office, we will account for the discontinuity so that we could fabricate a physical structure. Again, the design specs call for a maximally flat, low-pass filter with 4 GHz cutoff frequency with 20 dB attenuation at 7 GHz. We first calculate for the normalized frequency so that we could refer to figure 8.26 of Poisson as shown below. Our calculation shows that we need 0.75 normalized frequency, indicated by the red line or intersections with this red line will satisfy for a 0.75 normalized frequency, but we need a attenuation of more than 20 dB. The next step is to design low-pass prototype using lumped elements that will take the form of inductors and capacitors with 1 ohm normalized impedance. We will refer to table 8.3 of Poisson to find the values of these lumped elements. Highlighted in the red box, we can construct the circuit as shown in the slide. Notice that the purchase of this circuit is normalized to 1 ohm. We will scale this circuit later to normalize it to the requirement of 50 ohms. In order to make the stub design, we must first use Richard's transform to obtain the transmission line equivalent components of each capacitor and inductors. Inductors will take the form of short circuit transmission line stub with an impedance equal to its inductance, and capacitor will take the form of an open circuit transmission line stub with an impedance equal to its reciprocal of its capacitance. It's not ideal to have a short circuit transmission line in our circuit because it will require us to bridge our circuit to ground, which will require us to drill a hole through our microstrip substrate. We will use the CRODA's identities to design an equivalent circuit with only open circuit stub and regular transmission lines. CRODA A tells us that a couple unit elements and open circuit stub can be represented as an unit element, a coupled with a short circuit stub scaled to a factor of 1 over n squared of its original impedance, where n squared is equal to 1 plus z over z1, and CRODA B is just the inverse of CRODA A. Here we have our original circuit. We will place a 1 ohm unit element at the end since this circuit is already normalized to 1 ohm. To try and make an equivalent circuit with short circuit stub using CRODA's identities. With the unit elements attached at the end, we realize that we can make use CRODA A identities to obtain an equivalent circuit below. It looks as if we just inserted more short circuit stub, which we don't want, but we will try to attach another 1 ohm unit elements at the input and output to see if we could somehow get rid of all short circuit stuff at once. With the attached unit elements at the end, it is easy to see what we could utilize CRODA-B identity to reduce the required equivalent circuit with only regular transmission lines and open circuit stub.
Here is our original Kuroda simplified circuit. We multiply this with 23 ohms and convert each transmission line impedance to the required width for our microstrip substrate using Pulsar's equation in 3.196. Notice that the microstrip lines have widths and lengths of 40 mil and higher. This meant that the skinniest component of our circuit is just over 1 millimeter, which is definitely doable. Also notice that we did not implement our quarter wave impedance matching yet because we wanted to see the effects of the impedance matching in the end. To account for any effects of the short circuit stubs, we just used MLEF parts and tuned it accordingly to see if it had the same return loss of its original MLOC counterpart. There is clearly no difference in behavior due to the compensated end effects, as shown in the graph below. However, when tuning the T-junctions, we decided to tune it the way we had done it in our last project, where we isolated and tuned the elements that made these junctions away from the main circuit. Apparently, this led to really bad cutoff frequencies and made our gain go haywire. What we did instead was place the junctions one at a time, starting at the center within the main circuit, and use our gain graph to make sure we get an equivalent gain with these discontinuities. As you can see in our graph, we have a cutoff frequency at 4.1 gigahertz by doing this method, and a really good attenuation at 7 gigahertz at negative 39 dB. The weirder part came in when we used a quarter wave impedance matching at our input and output of our LPF in order to normalize it to 50 ohms. We suddenly introduced an equal ripple of about 2.5 dB at our passband, but we actually wanted a maximally flat band. After hours of tuning again and again of trying to reduce this ripple, we have found that the flatter we try to make it, the smaller our cutoff and bandstop frequencies became. It started to deter away from being an LPF into something really odd. So instead, we opted to keep the ripple no matter the magnitude of it, and tune our circuit based on the cutoff frequency and attenuation of our specifications. We got our attenuation to increase by 7 dB and keep the cutoff frequency to about 4.2 gigahertz. Notice that we did not forget the T-junctions where we place our quarter wave lines. Here is the layout laid out by MO's snapping feature, which we successfully got to print one-to-one. Stay tuned and see how that's done. Notice that it is perfectly symmetrical as shown by the red line. Also notice the T-junction compensation that Microwave Office drew up. It's what we thought how would they look like, but how MO came up with these dimensions is alien to us. We decided not to argue with MO and just print and hope to God that it would work out the second time around of fabricating our filter. Here's a picture of our filter that we fabricated. And these are the results, which shows our experimental versus simulations. The simulated cutoff frequency of no discontinuities and with discontinuities are both around 4.2 gigahertz. Shown in green are our experimental results, which came to around 4.46 gigahertz for a cutoff frequency. Not too shabby since our attenuation at 7 gigahertz and higher are still over 20 dB. So, in all, we can conclude that MO's layout are much better than how we originally designed our first filter to be. And we didn't really talk about our first filter because it came up with really crappy results. Alright, thank you.
Thank you.